Hi, today I will give a presentation for paper demonstration of virtual atom control mate quantum gates. In this paper, we give a demonstration of a control NOT gate between two individually addressed natural atoms using the Rydberg blockade interactions, and then they using the different gate factors HCZ control knot and the amplitude control knot measuring the control knot fidelities and getting the result 0 0.7 and 0 0.73 and 0.72, and they make achievement that natural atoms can held in the optical traps separated by a distance larger than 8 microns. Before I make the presentation, there's two basic concepts used in this paper. The first is the Rabi cycle. When an atom is illuminated by the coherent beam of photons, it will be cyclically absorbed as photons and we emit them by the simulate emissions. The probability is finding an atom in the excited states follow those equations, and means that the possibility is changed periodically. In the excited state, changed periodically. In this paper, the excited state is the state R, the Rydberg state, and the state 1 and the state R are coupled by a laser which have wavelengths of 780 and 480 nanometers. Another concept is the Rydberg blockade. And a Rydberg atom is an excited atom which has very large quantum numbers. So the two quantum numbers are placed approximately with each other. The ground state 1 and the Rydberg state R of each atom forms a two-level system that is coupled by a laser, and there is a Rabi oscillation with the Rabi frequency in this Rabi frequency. The key point is that the key point for the Rydberg blockade is that the excitations of one atom, say the target atom, depends on the state of another, say the controlled atom. And we just assume that we apply the 2-pi pulse on the target items. There was an excitation or these excitations which will generate a phase shift on target atoms. But if there is the control atom is excited to the Rydberg state before the applications of the 2-pi pulse on the target items, the dipole interactions shift the Rydberg level by amount B that will deter the excitations of the target atom. Then we will see nothing changed from the target items. Based on these properties, they designed the experiment, and the experiment can be divided into three parts. For the first part is to verify the loading atoms has ability to carry out the Rabi oscillation between the state 1 and the state R. They first localize the atoms to the region formed by the laser beams, and the laser controls the coupling between the couplings between the internal states. Then they start by loading single atoms onto the both sides. Then, and at last, they measure the target sites, target items with or without loading atoms on the control side to make a comparison. And here is the result of the first part. For the left is the oscillation of the target site, target atom without loading the controlled items, and the right side is the result with the loading of controlled atoms. So we can see the oscillation, the Rabi oscillation between the state 1 and R is influenced by the loading of the control items. So the items here in this configuration has the ability to carry out a Rabi oscillation between the state 1 and state R, the Rydberg states. After they demonstrate this, they do a second demonstration to demonstrate the Rydberg blockade. They use at first they do the same thing. They load the atoms to each side. Then they give a pi pulse on the control side. The pi pulse on control side to excite the control side atoms in control side to the Rydberg state. Then they give a Rydberg pulse of length t applied to the target side to make the change on the target side. Then again, at last, they again apply the pi pulse on the target side to let the atom return to the ground state. And then last, they measure the position of both sides. And here is the result for the second part. We can see that on the left is the result with no pulse on the control side, and for the result on the right, this is the result that there is pi pulse applied to the control side. We can see that the presence of the pi pulse applied to the control side reduce the possibility of the Eigenberg states for about 0.8 to 0.3. So after demonstrate this, then the last step for them is to apply the properties of the Rydberg blockade properties into the configuration of control NOT gates. They're using the HCZ control NOT gate and amplitude swamping control NOT gates. In this experiment, I will introduce the amplitude swamp control NOT C0 gate configurations. And they apply the amplitude swamp control NOT gate by apply the several pulses on the control and target sites in the special sequences. And first they generate a sequence. They generate a pi pulse to the target, to the control site, and then they give the 5 pulse to target site. Then they give the pi pulse to the control site. When control atom is initially in the 0 state and in state 0, and so in this situation, the control site atoms will be excited to the Rydberg level. So the pulse 2, 4, 6 are disabled. But if the initial state of control state is 1, then the pulse 1 and the pulse 7 applied onto the control side is disabled, and the pulse 2, 4, 6 and 3, 5 on the target side has effect, and they swamp the amplitude from 1 to 0 or 0 to 1. So after they finish this, they measure the matrix. Measure the matrix for the amplitude swamp gate and actually this CNOT gates, and they get a CNOT matrix with a fidelity of 0.7 and 0.73 and 0.72, and this is a great step for in the field. And the importance of generating gate like this is that they can generate the Bell states with fidelity, whereas at 0.48 and 0.006. And what they make another big achievement is that they can apply these experiments with the neutral items held in the optical traps, separate by a length larger than the 8 microns. This is another big step. So my presentation is over. Thank you.